Folks, picking up right where we left off. Okay, so changes in internal energy. Here we have this function u. U is a function of v and t. Okay, so we're going to start getting used to seeing these types of three-dimensional graphs. These are often referred to as a surface. So in this case, an internal energy surface. And we just finished that discussion of exact and inexact differentials, or state functions versus path functions. And here's two really good examples of that. Okay, so consider some initial state I, okay, given by ui, and which of course would have vi and ti, and then consider some final state uf, which would have vf and tf. Okay, and we know because u is a state function, when we take uf minus ui, this gives us delta u. But we also know, because it's a state function, the following is true. If I integrate it along that path from I to f, I'm still going to get the same result. Okay? So now, but what if we look at the path? Okay? So in this path 1, you can see that work was non-zero and Q is 0. So what does all that mean? Well, if Q is 0, that means it has to be adiabatic. Okay, so remember, Q is 0, adiabatic. Okay? Work is non-zero, that means it's expanding or it's compressing. And if we look at the way this is going on this landscape here, you can see that perhaps the volume is getting bigger, so that would be the adiabatic expansion. Okay? But now what about path 2? In path 2, work is non-zero, and the heat is also non-zero. Okay? So that means this would have to be in some type of diathermic container. Okay? And so path 2 could correspond to, well, it can't be free expansion because the work is non-zero. So this would have to be reversible work, but non-adiabatic reversible work. Okay? And the important point to note about these things is the paths are very different. So in other words, if I try to integrate Q along this path, this is not going to equal delta Q, okay? Because the heat done is very different for both of those two paths. However, we can say that this is true because U is a state function, okay? And so that's our consequence of exact and inexact differential expressions, okay? So we're going to shift here, and we're going to start thinking about how we can express the internal energy in terms of its variables that will give it that exact differential expression. Okay? So here we have the system, and outside of the system, of course, are the surroundings. And here, this also, by saying TV and P contributes to U, that's like the same thing as saying, let's make it different color so we can make this stand out. That's like saying U as a function of T, V, and P. We know that the internal energy is dependent on T, V, and P. Okay? So now we have to start taking advantage of these definitions of state functions, and we want to come up with a total differential expression for U. So we want to come up with an expression for du. And for now, we're going to choose T and V to make this just a little bit easier. But then we will also play with P, the pressure variable, soon. Okay, but let's just choose T and V for now. And so I'm not going to come up with any crazy like x squared times y squared cosine or whatever. We know that U is a state function. So I'm just going to define it with an exact differential expression. And I can do that via the following. I can say now the partial of U with respect to V at constant T dV plus the partial of U with respect to T at constant V dt. Okay, so I've built up my exact differential expression. Okay, exact differential expression. And now the game that we're going to play is inspect the derivatives and see if we can connect those derivatives to a physical observable. Okay, so we have changes in U with respect to volume at constant temperature and changes in U with respect to temperature at constant V. So does this look familiar? Yep. If you said that's CV, then you're correct. Pretty awesome, huh? Okay, that's CV. So I can now rewrite this equation, and I can say du equals this derivative at constant t dv plus cv dt. And what's pretty cool about this expression now is because we're holding volume constant, or at least let's suppose that, let's say we were to hold volume constant, then we know that this whole derivative drops out, and then we're just left with du equals cv dt, which we know is true, right? So that's pretty cool. Okay, so now what about this derivative? Okay, what does this mean? Okay, I'll put a question mark next to this one as well. So let's do a unit analysis and find out. Okay, so the partial of u with respect to v, all at constant t. So we know that u has units of joules, and I'm going to use the SI notation of volume. That's cubic meters. Okay, and let's keep going with this. So a joule is a kilogram meter squared per second squared. Kilogram meter squared per second squared. And then there's still that meter cubed from the volume. Okay, the meter unit and the meter units cancel, and we're left with a kilogram meter per second squared. And if you were to carefully inspect what a kilogram per meter second squared is, you would find that's a Pascal. Okay, so that means this derivative is a unit of pressure. It has to be. If it has units of pascals, it has to be some type of unit of pressure. Well, as it turns out, some very smart, famous people, Joule himself, gave this derivative, this unit of pressure, a special name. They called it pi sub t, which equals that partial derivative, and they call this the internal pressure. And we'll see what that means, okay? Internal pressure. Excuse me. Okay? And we're going to see some consequences of what this internal pressure is. Okay? But all the same now, we can actually rewrite our exact differential expression of u. We can replace those derivatives with their corresponding physical observables, which is pretty cool. So I can say now that du is pi t dv plus cv dt. And that's a much nicer equation to look at than all of those nasty derivatives. Okay? We're going to see some other consequences of these derivatives as we move forward in the class. So we're still going to play with these partial relationships. But for now, we can see that just by making an exact differential expression in u and taking advantage of just that mathematical definition, we extract physical observables that are dependent upon the internal energy, such as the constant volume heat capacity. We know that's dependent on internal energy, or really we should say internal energy is dependent on the constant volume heat capacity. And similarly, this internal energy is also dependent on what we call internal pressure. Okay, so what is this internal pressure? So we introduced the Joule experiment, which I will say as the discovery of, oh, that doesn't look like pi t. It looks like a hashtag. So this is the discovery of this pi t parameter. Okay. So what Joule did in this experiment, he had high pressure gas on one side and vacuum on the other side, surrounded by a giant water bath, okay, in which he had a thermometer. Yes, I did say a thermometer, the requisite instrumentation for measuring thermos. Okay, so what Joule did in this experiment was he expanded this gas from high pressure into vacuum and thought, okay, if there's some type of interaction between these particles. So the whole idea of ideal gas law and real gases was kind of still being worked out at this time. Okay. So, but he said if there's some type of interaction between these particles, as they expand away from each other, there should be some type of temperature change as a result in the conversion of potential energy to kinetic energy, fueling the separation of the gases. Okay, but and so he didn't measure any temperature change at all. So there was no delta T in this original experiment. Okay, so in other words, he concluded that there was no heat transfer. So there was no heat transfer from the gas to the water. Because remember, he's measuring the temperature change of the water bath. So he concluded Q has to be equal 0. Well, this is free expansion. It's expansion into vacuum. Okay? So therefore, work has to be equal to 0 as well. So if work is equal to 0 and heat is equal to 0, we remember the first law of thermodynamics that says delta U is work plus heat. So he also concluded delta U must be 0 in this experiment. Okay? And if we go back to that expression we came up with for U, I'll write it up here at the top. So du equals pi t dv plus cv dt. Okay, he said, well, look, if dt is equal to 0, because there's no temperature change, and dv definitely is not equal to 0, so I'm going to write that down. dv is a finite value, right? The gas changed volume. However, because du was all equal to 0, then he concluded pi t must be 0, and later that was refined. Pi t equals 0 for an ideal gas. Okay? So in other words, there is no internal pressure of an ideal gas. And what does that internal pressure mean? Well, that's related to the attractive or repulsive forces that gases have on each other that influence a change in pressure relative to the ideal value, like we talked about with gas laws. Okay? It can also be shown later. We're not going to do this now, but it can be shown. We'll do this later on in a few weeks. Pi t equals, this is really cool, A over Vm squared for a van der Waal gas. So that's really, really neat. So that is that collisional term, right, that gives us the internal pressure dependence of a real gas. Okay? And also, so let's go back to the basics of that definition. Pi t we recognize was the change in U with the change in V at constant t. So I can make a graph out of this relationship. Look, U versus V. All right. And so the slope of this graph will be pi t. So in other words, right, if I expand this, I can say du equals pi t dv. Okay? So now when I get this graph here, right, we can see two regimes will manifest as a result of the volume. Okay? And so it depends on the conditions. We know that when pi t equals 0, so in other words, when the slope is 0, right, this is a slope. So slope equals 0 for a perfect gas, so no attractive or repulsive forces. However, if we're in a regime here where pi t is greater than 0, we kind of have to think about why a positive slope of this would lead to attractions and why a negative slope of this would lead to repulsions. And you have to consider what's happening as a result of the change, okay? So let's play with these repulsions. This idea of if pi t is negative, it's an indication that repulsive forces are dominant. So if we're starting here at this really small volume and we end here at a larger volume across, let's say, this expansion, right? This is expanding, okay? If as a result of expanding, the internal energy decreases, we know in that initial state, repulsions must have been dominating because those repulsions have the effect of raising the internal energy of a gas. And so if we're expanding these gas particles and the internal energy is dropping to a more favorable outcome, then we know from that initial condition repulsive forces must have dominated. Okay? So now similarly, if we're in this initial condition down here, and by expanding the gas, it has the effect of increasing the internal energy, then what that means is those particles, those gas molecules, were happy being next to each other. They had a very low internal energy. But as we separate them out, if their internal energy increases, they're kind of responding and saying, I don't want that. I want to be close to my neighbor, so I have to increase now my potential energy as you're separating me out. Okay? So that ends up being the result of this internal energy. So it again, it depends on a parameter we haven't put in here, which is pressure. Okay? So pressure will dictate where we're at in this regime of repulsions or attractions. Okay? So moving on. Okay? And then so now what I also want to say about this, when we're playing with these derivatives, there's a few other things that end up manifesting, a few other physical observables. And I'm not going to derive these directly, but I'm just gonna briefly talk about them. So I'm gonna go. I had to give myself another page here. I ran out of room. Okay. So now we know that du equals pi t dv plus cv dt, and that was a result of partial of u with respect to v at constant t dv plus the partial of u with respect to t at constant v dt. Okay? And so we know when we did that, we got these two physical observables, constant volume heat capacity and internal pressure. So what about P? Okay, what about dP? So now I'm going to look at the total change in U with respect to P. So we're just going to apply the change in P to this whole expression. Oops, wait, hold on a second. What did I do? How does internal energy vary with temperature at constant pressure? Yes, so apologies. That's what we want to do. What about dP? So excuse me. So for now, I apologize. Let's think about how we have to. So we've held volume constant, we've held temperature constant. So now we're going to hold pressure constant. So I'm going to look at it in this way, okay? And you'll see why momentarily. Because what it does, I'm going to keep this pi t. So now this is going to give me partial of v with respect to t at constant p. So that's why we're going to do dt at constant p. Because this is the last, if you think about that reciprocal identity that I talked about in lecture 11a, this is the last variance that we have to do. Okay? And then now dt over dt cancels, so that ends up just being plus cv. Okay? And so now we're going to play with this relationship, partial of v with respect to t at constant p. And as it turns out, that's the slope of Charles' law. Okay? And so there's some other physical observables that manifest from this partial of V with respect to T at constant P. So just like we got out the constant volume heat capacity and the internal pressure, there are two more physical observables. I'm not going to derive them directly. I'm just going to kind of show you the result. But they are a manifestation of thinking about how the volume changes with respect to temperature at constant pressure, or, right, even as we know, how does volume change? So let's chalk that up. So we can say this, or how does the volume change with respect to pressure at constant temperature, right? If I switch the order of those two parameters. And so the result of that is two of these coefficients, one known as the expansion coefficient, one known as the isothermal compressibility. Okay? And so again, I'm not deriving where these come from, but you will notice they contain that relationship. So the expansion coefficient is a result in the change in volume with respect to temperature at constant pressure. So in other words, the expansion coefficient gives us how the volume of a sample changes with changes in T, right? So as we heat up a material, we generally think of it as expanding, right? As we cool the material down, we think of it as compressing, okay? Similarly, we have this thing called the isothermal compressibility. And you notice now, this is looking at how the volume of the sample changes with respect to changes in pressure. So volume of sample changes with changes in P, okay? And so I've got some representative materials here. Benzene, diamond, lead, and water. And let's think about what these things mean. So if I compare the value of benzene to the value of diamond, and this is the alpha coefficient, what does a big alpha mean? What does a little alpha mean? Well, for benzene, a big alpha means that benzene is going to be sensitive to changes in volume with respect to temperature. So if I take a sample of liquid benzene and heat it up, we're going to see changes in volume to the benzene much more than we're going to see the changes in volume of the diamond. And that makes sense, right? Benzene is a liquid at room temperature and pressure, right? So these are the values at 298 K. So it'll be much easier to expand a sample of benzene than it will be to expand a sample of diamond. And we're not talking about a whole lot of expansion. Look, this value is 10 to the negative fourth per Kelvin, okay? So these are small values, right? So that alpha, you know, is 12.4 times 10 to the minus 4, okay? So now what about isothermal compressibility? So again, compare benzene and compare diamond. It's really the same thing. It's saying that at constant temperature, I can squeeze the hell out of a sample of benzene and get a much more noticeable volume change than I can for a diamond. And that makes good sense, right? That makes really good sense, okay? So let's see. So I'm just going to very quickly show you how we can use this in calculations. So and I'll just do that for the isothermal compressibility, okay? So I'm going to rewrite this here, and I'll show you how we can take advantage of the fact that this is a partial and what we can do with it. And so this is what I call divide and conquer. So let's get the like terms with like terms, okay? And so I'm going to put over on this side negative kappa T dP equals dV over V. Okay, so I just separated those out. And then now what I can do, I'm going to do my work over here. I can integrate from initial to final of negative kappa T dP. And I can also integrate from initial to final of dV over V. Okay? And so what do I get? Well, over here, on this side, I'm going to get a kappa T times delta P. Right? Pretty straightforward. And so what am I going to get over here? And so, sorry, there's a negative sign. Well, here I'm going to get natural log of VF over VI. So how can I make that useful? Well, take E of both sides, okay? And so when I take E of both sides, I'm going to write this way down here. I got E to the negative kappa T times delta P. All right, so I'm going to keep that there. And when I took the E of this side, it's VF over VI. And I'm going to do a couple algebraic steps, so make sure you're okay with this. So then I'm going to move VI over to this side. So that's going to go in front of the exponential. And then finally, that's VF. All right, cool. So now what this formula gives me is a way of calculating what would the final volume be, given that I know the initial volume and the change of pressure, right? And I can do the same thing for the expansion coefficient. And what you would find for these things like benzene, I mean, you know, we talk about these like liquids and solids being the, you know, incompressible fluids, right? Well, I mean, if you isothermally compress a sample of benzene with 1,000 atmospheres, so if I make delta P 1,000 atmospheres, you can noticeably compress that liquid. You can shave like 10 milliliters off of a liter volume of benzene with 1,000 ATM. That's kind of impressive when you think about it. We normally define these liquids as incompressible fluids, but given enough pressure, we can squeeze the hell out of these things, okay? And obviously, you know, you can tell that benzene, you know, it's like a factor of 100 greater compression than diamond. And right, similarly, it's a factor of nearly 1,000. 1, 2, 3. Yeah, it's nearly 1,000-fold in the expansion. All right. And so there's some nice intermolecular forces that we could talk about going on here. You also notice that water is not nearly as compressible or expandable as benzene, and that's due to the hydrogen bonding network, right? Benzene is like, you know, flat, right? Like we can stack it up, okay? So benzene is fairly compressible as a liquid. Okay, I'm going to move on. Okay, so now, similarly, just like we did with U, what happens if we repeat this with H? Okay, so system, surroundings. We're also going to say H as a function of TV and P, and we're going to try to come up with an exact differential expression for H. And another thing to give you the historical context, so here the Joule Thompson effect. So I talked about in the Joule experiment how it was largely a failed experiment, even though sometimes failed experiments give us noteworthy results, such as the internal pressure of an ideal gas is 0. That's a noteworthy result. Joule did want to show that through the expansion of gases, you could measure their real behavior. And so he teamed up with William Thompson, aka Lord Kelvin. Yup, same person. William Thompson of the Joule-Thomson effect. Alter ego is Lord Kelvin. There's some cool history there. Do a wiki search on Lord Kelvin, aka William Thompson. Neat stuff, interesting history. Okay, and so what they concluded, and I'm not going to spend a whole lot of time with this because it gets into the weeds and the details of the math, but what they concluded was if they can do this experiment in isenthalpic conditions, which they showed has to be done adiabatically, this experiment, okay? So in an isolated system, then they could measure the real behavior of gases as they're expanded. And let's go through that. Let's build this up, this exact differential expression of enthalpy, and talk about how when this Joule-Thomson experiment was repeated, it did lead to the first measurements of non-ideal behavior in gases. Okay, so let's build it up. And for now, I'm going to choose T and P for H, and then we'll put in that third variable and see what happens. Okay, so we're going to say partial of H with respect to P at constant T dP plus the partial of H with respect to T at constant P dt. And now we play the same game. We have this exact differential expression, and we look to see if there are physical observables that are a result of this game we're playing. And the answer is yes. Partial of H with respect to T at constant P is Cp. That's the constant pressure heat capacity. Okay? So we can rewrite this and say partial of H, and for now I'll keep that partial of H with respect to P at constant T dP. And that's going to be Cp dt. And now in the same way we talked about this, right? If the pressure is being held constant, then this whole first term drops out, right? And then just dH equals Cp dt, which we know is correct. Okay? So I'll remind you here, the twins, du equals Cv dt, dH equals Cp dt. And of course, this is at constant volume, and this is at constant pressure. Okay? Those are the twins. Keep track of the twins. Okay? So now, what happens here? Well, Joule and Thompson had concluded that they needed this experiment to be isenthalpic. And the reason for that is to eliminate variables. Okay? So for example, if this is all isenthalpic, right, if all of that equals 0, then we can start setting this derivative equal to this derivative because we know that they should be equal because it's an exact differential expression. And we can see what manifests as a result. All right? So I will now write that as partial of H, partial of P, constant T, dP equals negative Cp dt. So I just subtracted Cp dt over to the other side. Okay? And now, if we look at how, so we talked about how, let's see here, let me think the best way to describe this. Okay, so now what I want to do is try and eliminate some more variables. Okay, so if I want to know, for example, how maybe the temperature changes with pressure at constant enthalpy, we're going to divide both sides by dP. Okay? We can do that in this algebraic manipulation. So now I can say that the partial of H with respect to P at constant T, right, I eliminated the dP to make life a little bit easier. This now equals Cp by the partial of T, partial of P, and on this derivative, I'm going to say that that was done at constant H. Okay? And as it turns out now, this derivative is very useful. Partial T with respect to partial P at constant H, we call this the Joule-Thompson coefficient, the JT coefficient. Okay? And so there's a couple different ways that we write that. We can write that as a partial of T, partial of P, H. Okay? And it's given the Greek letter mu for the Joule-Thompson coefficient. But we also know, because this is based on exact differential expressions and state functions, that we can just simply write this as delta T over delta P, or in other words, T final minus T initial over P final over P initial, which are two things that we can very easily measure, which is really cool. And so now finally I will rewrite our expression in H as dH equals Cp dt minus, so that's going to be mu Cp dP. So we've dropped all those derivatives, and now we have a total differential expression in H for things we can easily measure, like the change in pressure and the change in temperature. Okay? And another thing that we see that's very cool, what manifests out of this, we can see some natural variables that take place. Okay? And those natural variables are the following. H is a function of T and P. Okay? What about U? Let's go back and look at that expression for U. Where did it go? Aha, U is a function of V and T. Okay, this is going to come back later on in our discussion of the twins. U is respect to T and V. Okay, we're going to see the manifestation of that. Okay, and now finally what I want to do is very briefly describe the Joule-Thomson coefficient, describe the Joule-Thomson experiment. We do the Joule-Thomson experiment in Chem 363 lab. This is definitely what can be a favorite of people. If you like working with high pressure gases and programming, we program the temperature measurement on a computer. So you have to have a very sensitive temperature measurement to do this. Okay, but I want to describe how Joule and Thompson were able to work this out, how to give this experiment isenthalpic conditions. And they figured this out by doing a flow of gases. So in that original Joule experiment, it was static. So there was one static chamber and another static chamber, opened it up, all the expansion happens, and then it's done. In the Joule-Thomson experiment, there's a constant flow from a high pressure side to a low pressure side. So imagine I've got a tube here, okay, and that's what's pictured down there, right? And I'll describe how the picture of the tube differs from the picture that I'm drawing, okay? So, and I'll say high P and low P, and you have this tiny little open nozzle that we call a throttle. The throttle is the key in the Joule-Thomson experiment. So you have some set of initial conditions over here, and it's drawn like a piston, and you can approximate this as a piston to prove that it's isenthalpic, and I'm not going to spend a whole lot of time with that. All I want to take note is we have some initial condition, okay, where Pi is always going to be greater than Pf in this situation. And that's because typically Pf is open. So this other side of the throttle is open to the atmosphere. And because you have this throttle, it limits the flow of gases. So it allows pressure to build on the other side of that throttle. It's what we call differential pressure, where it's technically open. This is technically an open system from one side to the other. Mass and heat can be exchanged from the initial chamber to the final chamber. However, because this throttle is tiny, it makes like a stopgap or like a plug, if you will. Okay, so it has a throttling effect. Okay, and so the result of that, and I'm not going to go through this math proving this is isenthalpic. Follow it along in the book or my notes. Okay. So, but what's the result? What's the result of having this throttle? Well, I'm going to demonstrate that for you right now. Okay. So I'm a big gas bag full of hot air. That's the truth. There it is, right? I can feel all of these warm gases because my body is warm. And I'm expanding those gases out into the atmosphere. And I can feel the warmth on my hand. What happens now if I make a throttle? Right? Same temperature. My body hasn't changed temperature. Now what does it feel like? It feels cold. Do this. Try this. It feels cooler. I am actually throttling the gases as they expand out of my lungs, and it is cooling them down vis-a-vis the Joule-Thomson effect, which is really, really cool. Okay? So what does all of that mean, and what's going on with this? Okay, well, we said Joule-Thomson mu is partial of T, partial of P at constant H, which is the same thing as saying delta T over delta P, or which is saying T final minus T initial over P final minus P initial. Okay? And so as it turns out, not all gases cool when they expand, but the vast majority of gases do. Okay? And so because the vast majority of gases do cool as they expand, what's the explanation? Well, the explanation is They're intermolecular forces. They're non-ideal behavior. As you are trying to separate them, okay, they are attracted to each other. And because they're attracted to each other, it takes energy to pull them apart. Well, because this is done in an adiabatic container, there's no available energy other than the molecules' kinetic energy themselves. So when you force them to expand over this throttle, so when you create this constant flowing experiment, where the initial pressure is greater than the final pressure, where the whole thing is adiabatic and isenthalpic, you will see molecules cooling themselves down to expand. And that is a result of non-ideal behavior. Here it is. Just creating that throttle gives you that behavior. It's really, really cool. Okay, so what does all this mean? Well, what happens when mu is greater than 0? What does that mean? And what happens when mu is less than 0? What does that mean? Okay. Well, think about this. Because in this experiment, Pi is always greater than Pf, okay, the delta P is always negative in this experiment, right? So that means when mu is greater than 0, you have a negative delta T, and so thereby there's a cooling effect. And when you have a mu less than 0, you have to have a positive delta T, thereby it's a warming effect. So when would a gas cool upon expansion as a result of Joule-Thomson? And when would a gas warm? Well, a gas would cool if attractive intermolecular forces were dominant, right? Because if attractive intermolecular forces are dominant, they're like they want to be next to each other, so they have to use their own energy to expand, and because it's adiabatic, they expend their kinetic energy, which allows them to cool down. So, but if a gas warms upon expansion, repulsive intermolecular forces are dominant. Okay? And so, as it turns out, the boil temp is an okay predictor of this. The inversion temperature is better. And I'm not going to draw up the formula for the inversion temperature. I will define that it's typically given as Ti. The inversion temperature is the temperature at which a gas switches signs and its Joule-Thomson coefficient, and it is fairly closely related to the boil temperature. Okay? So for example, most gases, if not all gases, at room temperature cool upon expansion. The only ones are helium and hydrogen. Helium and hydrogen warm upon expansion at room temperature, but just barely. As it turns out, helium and hydrogen are very damned difficult to measure undergoing a Joule-Thomson effect because they're practically ideal over most conditions. However, molecules like carbon dioxide have humongous Joule-Thomson coefficients. Okay, so CO2, the mu for CO2 is roughly 1 Kelvin per bar. So, right, it's delta T over P, so the units are Kelvin per bar. And so what that means is for every bar that a sample of CO2 is expanded, it cools by 1 Kelvin. So consider now an old school fire extinguisher that actually has CO2 in it. Not the dry, the powdery stuff, but an actual old school carbon dioxide fire extinguisher. Those things are shaped like this. Let's see if I got another picture. Okay. So CO2. Oh my God, I can't write. So a CO2 fire extinguisher, I'm just going to draw a picture of it. And if you've been watching the notes, you know what I'm talking about. So here it is, right? It's this nice little fire extinguisher. It's red. If you've never had the ability to like shoot one of these things off, then you haven't lived yet. And so these things have this big open throttle, right? It's this big conical thing that gives you a throttling effect. So it's very tiny right there, and it opens wide up to allow the gas to expand. Okay? Well, these things, so PF here is going to be roughly 1 atmosphere. But PI, so like here's the regulator nozzle, right? PI on these tanks can be like several hundred atmospheres. So let's say like 300 atmospheres, or even let's make it a little bit more realistic here. Let's say like 200 atmospheres. Okay. So what that tells us is, because we know the Joule-Thomson coefficient, delta T over delta P for CO2 is about 1 Kelvin per bar. If you expand this thing by 200 atmospheres, so you just open this thing, you let it throttle right out into the atmosphere, it's going to drop 200 Kelvin. It's going to get really, really damn cold. And it'll put out a fire. We'll prove this in the laboratory. We will do this in the lab. And if any of you have ever had the benefit of seeing the physics rocket car, they do this exact thing with an old school bottle of CO2. And it drops the temperature so much that you get ice, right? It freezes out the water in the air. You can see this Joule-Thomson everywhere, right? That's a Joule-Thomson effect. For those of you, if you like to barbecue with a propane tank, as it turns out, propane has a fairly large Joule-Thomson coefficient. And when you open that propane tank, that high pressure propane tank, and it expands out into the burner, the tank gets cold. And the tank gets cold because it's undergoing a Joule-Thomson expansion. Okay, so this is very, very cool. I do have an activity right here. I think I pretty much covered all these things. Answer these questions. I pretty much covered them all. And I'm going to sign off because right now it's 10:52 a.m. on a Friday, and we are going to meet live in 8 minutes. But you probably will not watch this video by then, and that's okay. All right, folks. I'll see y'all soon.